So the next presentation was going to be given by Andrew Jordan, but we have Jody here who's going to give it on his behalf, and it's on a framework for the history of the moon's polar ice.
So, look at that. So, that's pretty neat. Okay. Before I begin, I have one odd question. Does anybody happen to know the identity of the bird whose call we're hearing outside? Whose call is able to pierce through your hotel wall at 3:30 in the morning? Beep, beep. No one? No bird watchers? Okay. Just curious. Let's see. I need to back up here. All righty. So I'm Jody Wilson, standing in for Andrew Jordan. We're both on the crater team, the Cosmic Ray Telescope for the Effects of Radiation. This work is really Andrew Jordan's brainchild. So if you have any particularly deep questions, I may have to reference you to him, but we'll see how I do here. I think it's fair to say that when most of us think about ice at the lunar poles, and I'm going to use ice here interchangeably with hydrogen or hydration. I'm not going to try and pretend like I know exactly what the form is, but let's say ice just for the sake of this talk. When we think of ice, we think of it in terms of a patchy distribution, it's in PSRs and not so much outside PSRs. And even if you look at particular PSRs, for instance, here you look at a map of neutrons, it's particularly abundant in these two craters, but then if you look at a map of surface frost, now it's more abundant in this crater and not in the ones that were showing up neutrons. So it's very heterogeneous. So I want you, for this talk, to step back and look at the bigger picture, a larger spatial scale. And here is something we saw 2 talks ago, if you don't recall. This is now Lunar Prospector neutron maps of both poles, and there are 2 concentrations of hydration at each pole. One concentration centered on each pole, shown in the dashed circles here. But then there's also at each pole a concentration offset from each pole, surrounded by the solid circles here. And what's interesting about these is that they are basically antipodal. These 2 offset hydration patches are at about the same latitudes. They are at approximately opposite longitudes, and they even have approximately the same peak hydration abundances. So the idea is that these indicate that the moon's rotational axis was slightly offset earlier in its history from what it is today. We call this the paleopole. And so at that time, these were the, here, one back. These are the poles, hydrogen or ice was being deposited there, new modern locations. So on this larger spatial scale then, it looks like we can actually constrain some of the sources and losses of ice in an important way. And one way to look at this then, I'm going to show several little diagrams of one of the moon's poles. The modern pole shown by that yellow dot, and the 70-degree latitude line shown by the yellow circle. I'll indicate why 70 degrees is significant in a couple slides. And if all we had was ice deposition early in the moon's history, when the axis was offset, then you're going to have this oddly offset ice cap that does not line up with the current pole. Now, if the pole shifts and then all of the old ice that is now suddenly equatorward at 7 degrees gets too warm and is lost, you're going to have this odd football-shaped ice cap with one boundary being the new boundary, one boundary being the old boundary. Now, if further we start to deposit modern ice on top of that, you'll get now a nice round ice cap, but with the maximum perhaps still offset from where the modern pole is. But then if you deposit a whole bunch of modern ice, or maybe the old ice cap goes away, you end up with a perfectly symmetrical ice cap like you would expect. Another way of looking at this is basically that we could be looking at simply 2 combined ice caps, an old, more buried ice cap, a more modern ice cap closer to the surface. Now, why is 70 degrees critical here? I'm not going to show you several data sets that explain why. Let's start with LRO lamp. This is a plot of the ratio of two ultraviolet bands or reflectances versus latitude near the South Pole. And each little black dot is a small pixel on the moon, and then the blue squares are averages. And the idea is that when the ratio between these two ultraviolet bands is higher than 1.2, that indicates some level of frost coverage, either intermixed with the regolith or perhaps a surface layer. So you notice as you head towards from about 76 degrees south in this case, towards the pole, you get more and more of these black dots above the critical ratio, and the average is also going up as you get towards the pole. And now, presumably some of these spikes here are actual PSRs, but the thing is, this trend also holds outside PSRs, which is interesting, so that makes you think more of a polar cap. Now let's look at something different. This is Chandrayaan M cubed, looking at near infrared, a particular absorption feature, again, which may or may not indicate water, but some form of hydration, presumably. Now you see that this feature is basically absent in between 70 north and 70 south, but poleward of 70, it shows up suddenly. So once again, this critical threshold of 70 shows up. And finally, let's look at two neutron plots. This is both from Lunar Prospector and LRO Lend. And now we're looking at the neutron counting rate versus orbital phase, and this is an orbital phase for polar orbit. So we have the equator, a pole, equator, and the other pole, and then the equator. And again, there's a boundary right at 70 degrees. Particularly, there's a couple spots here where it's just pretty amazing. You've got a sudden drop off of neutrons or a sudden increase in hydration right at 70 degrees. Now, finally, let's look at Crater, our instrument. We look at very high energy albedo protons, and the idea is that albedo protons are sort of the flip side of the coin with what you see in neutrons. So when you have cosmic rays impacting the lunar regolith, breaking apart heavy atomic nuclei, secondary neutrons are propagating up, and if they encounter a layer of hydration near the surface, the neutrons will hit a proton. The neutrons either slow down or stop entirely, energize a proton, which then travels up out of the regolith. So if you have a neutron detector up here, they're going to see a reduction in neutrons over a hydrated layer, in other words, over the pole, whereas we, in theory, would see an increase in albedo protons. And so over here on the right is our first stab, a very low resolution plot of a albedo proton yield versus latitude. And wow, this thing even just vibrated. So it's misbehaving. And anyways, that point right there, that's the highest yield of albedo protons, and it's nearest the pole. Not exactly proof that there's a cutoff at 70 degrees, but we have two new methods now of reducing data we're going to throw at this and hopefully get a much better latitude trend. And we also have more data to look at. So, in summary, on large scales and multiple data sets, you see what appears to be, if you will, an ice cap boundary at 70 degrees. And this was predicted a long time ago, the first time we considered even microscopic, not microscopic, but very tiny PSRs as a function of latitude. Now, because we're looking at multiple data sets, which are looking for water in very different ways, and they all see what appears to be an ice cap boundary at around 70 degrees, it's a pretty good indication that they're looking at the same thing, and that it's sort of, we could be looking at one large feature here. And if we can really synthesize these data sets, looking at the same features, we can really start to constrain perhaps sources, losses, and timing of the hydration in this polar cap. And in particular, it might be useful to look at a map of the moon mapped not in the modern latitude and longitude, but in the paleo lat and longitude, and see if that paleo cap actually pops out. And finally, for future work, for the Crater team, we're again, we have new methods now for analyzing data that one was in the works. I'm not really allowed to talk about it until it's published. That's going to happen very soon. And also, we're going to do some of our special horizon observations of the lunar pole, which we haven't done yet, which allows us to see actual depth resolution in our data. That's it. Thank you.
So we have time for questions. Microphone.
Reconcile the lack of water in some of the permanently shadowed craters? Comment on that?
Well, again, I'll just be conversational. This is not authoritative at all, but the way I think about it is that, particularly if there is an ancient ice cap, then in a sense, when a new crater forms, it's going to excavate some ice, it's going to redeposit some ice. So in one sense, you can sort of think of it as a piece of Swiss cheese, but then in terms of a crater that has additional like excess ice in it, that's where it gets a little more complicated. That's, I don't know how to explain that necessarily in terms of something happening to an ancient cap. Yeah.
This may just show ignorance, but is the polar wander steady or sudden?
My understanding is that it was sudden, that it had to do with the Procellarum formation and filling in. Yeah. Because that's the direction that the tilt happened, was in the direction of Procellarum. Yeah.
Any further questions? All right, let's thank our speaker again.